I got cut off when trying to start talking about Quicksort. Quicksort is a great sort. Here's the idea. I give you the collection of things I need sorted, maybe just like a list of things that need to be sorted. And in order to sort it, what I'm going to have you do is shuffle it, and then check if it's sorted. If it's sorted, you're done. If not, shuffle it again. Now, you're probably thinking this is a horrible idea, and you're right, it's a horrible idea. Let's think for a second, what's like the computational complexity of this thing? Like how, worst case scenario, how long will it take? And remember, it is possible to shuffle the deck of cards and have it that the cards end up in the exact same permutation more than once. Like that can happen. Now, there's two parts to this algorithm. There's like the shuffle bit, and then there's the check if it's sorted. Checking if it's sorted is easy, right? You go through the list and make sure everything's in an order, and if it is, you're done. And how much work is checking if something's in order? Well, it's just linear. It's however many things there are, we check it. Great. But the fact that I might have to shuffle like forever, that's going to be problematic because it's possible that this algorithm will never end. It's possible, exceptionally unlikely, that I shuffled the deck or the collection of things a billion times, and every single time I get the exact same permutation, which is not sorted. Now, when n is small, you will find solutions in practice, but as n gets big, this quickly becomes absolutely useless. So Quicksort is kind of a silly little sorting algorithm. Anyways, yeah. So here's one I actually really like that I use frequently. It's a simple idea, and I'll explain it with an example. At the end of the semester, I would typically have n exams I want to sort alphabetically. Okay, so at the end of 162, students will write the exam, I'm going to have their papers, not this year apparently, but I'll have these n papers, and I want to sort them. I want to sort them in alphabetical order. But here's the thing. I want them to be in alphabetical order. And if I were to use any of the other sorting algorithms we looked at, I've got a worst case scenario of n squared. Not that bad for like the 70, however many students we have in the class. Okay, there'll be a bunch of comparisons. But like 70 squared, that's a lot of comparisons. Now, with a very simple concession I can make my sorting algorithm very, very easy. How about this? I want the exam sorted in alphabetical order, but I'm okay if it's not perfect. Basically, here's what I'll do. I want to have all of the A's before all of the B's, before all of the C's, before all of the D's, before all of the Z's. Okay? So what I want is all the people whose last name begins with an A, I'm going to put here. So here's what I'm going to do. I'm going to take the top exam. I'm going to find what their last name is. Their last name might start with a D. So I put that exam here. I don't know, I'll draw a circle there for whatever reason. I look at the next exam, oh, their last name starts with a Z. So I put it here. Then the next one, oh, it starts with an A. So I put it here. How many times am I going to have to do this? Well, there's going to be n exams I have to look at. So I have to look at those n things. Okay. So for each one of those things, how many comparisons do I have to make? Well, I need to find where it goes. And if I do a simple, if I implement this very simply, there might be a better way to implement this, but if I implement this very simply, I will be like, okay, I'm looking for Z. And I'll be like, okay, is this Z? No, it doesn't go here, it doesn't go there, it doesn't go there, Z. What we will do, okay, I'm going to call these things buckets, for example. And I have K buckets, where K is, well, however many things I want to sort them into. So in this case, K will be 26, because there's 26 letters. And N will be, well, however many exams there are. So for each exam, I have to make at most K comparisons. So it's going to be N times K. And k, a lot of times, is going to be some constant value. So really, it's going to be k times n, but k is some constant. Do we care about constants? Not really. Suddenly, we have an order n sorting algorithm. And if you can have a linear time sorting algorithm, that's amazing. That's way better than n squared. But of course, there is a giant catch. With this algorithm, I will have all the A's before all the B's before all the C's. But I have no guarantee. In fact, it's unlikely that the A's within this A bucket will be sorted. They're going to be not in order. But you know, for me, for my purposes, maybe there's like, I don't know, 4 people in the class whose last name starts with an A. I don't really care if they're not in order. I want the A's. And the reason I want it sorted is because when students come, they want to look at the exams, I want to be able to find their exam quickly. And it's okay. I will concede that these don't need to be in order. As long as the buckets are in order, I'm happy. So this is a sorting algorithm, but the way I'm explaining it, I'm not guaranteed to have it completely sorted. It's just mostly sorted. And for me, I don't care if it's not completely sorted. I'm happy that I can sort those exams in linear time. Really easy. And then, by the way, that's literally how I do it. What I'll do is I'll put all the exams on the ground and I'll have an A pile, a B pile, a C pile, and so on. That's it. So this is a great sorting algorithm if you don't need it completely sorted. So here's the example I literally just said. All right, now, for those of you that came from 161, I have talked about Quicksort before. I talked about it very high level, but now that we spend more time doing recursion, maybe it'll make a little bit more sense. And these, by the way, the sorting algorithms that we're about to look at are a lot more sophisticated, but they're a lot better than the previous ones, all the n squared ones. So here's the idea with Quicksort. There's 2 big catches, not catch, 2 big interesting points we need to observe. One, a list that is empty is sorted. And the reason we'll say that is because that list, there's nothing out of order inside that list. And similarly, a list that's only size 1 is guaranteed to be sorted as well, because that one list is not out of order. Basically what I mean, imagine I have a list, and it's got some number, I don't know, 7 in it. Is this list sorted? Of course it is. Nothing's out of order. We're good. It seems silly, but that's an important catch. So the first big thing here is an empty list, and a list of size 1 is sorted. The other thing, too, here's the other catch. Catch, again, I'm saying catch. I really don't mean catch. I mean interesting observation. Imagine for a second, I have a list that's over here, and it's sorted. I don't care how it got sorted, it's sorted, okay? So I've got a list over here, it's sorted. I've got a list over here, that's sorted. And I've got what I will call a pivot right here in the center. Pretend I'm the pivot. So what I'm going to do, here's the thing. I've got a list over here of integers, whatever, something that we can order. A list of integers. And all of the integers over here in this sorted list are less than me. So if I'm the number 50, I've got a list over here of numbers that are less than 50. And they're sorted. It's guaranteed to be sorted. I don't care how it's sorted. I know it's sorted. So if I have a list of things that are less than me and they're sorted, and I also have a list of things that are greater than 50, greater than me, the pivot. So if I have a list of things over here, that's also sorted. I don't care how it's been sorted, I just know that it's been sorted. If this is sorted and they're all less than me, this is sorted and they're all greater than me, if I took this list, put me, I append it to like the end of that list, and I take this list and append that list here, what do I have? Another sorted list. Here's what I mean. I've got a pivot 50. Over here I have a list of things 4, 12, 31. And I've got a list of things over here that are also sorted. 51, 101, and 102. Arbitrary numbers, don't think they mean anything. If I just take this list, add it to it, and like kind of like add them together, append them, concatenate them, I will end up with a bigger sorted list. So the two interesting observations, the two important key ideas for Quicksort is an empty list and a list of size 1 is sorted, always, and if I have a sorted list of things less than me and a sorted list of things greater than me, and I do this, I get a bigger sorted list. That's it. That's the key idea. That's it. That's all we need to know. And if we know that, here's going to be my algorithm for Quicksort. You're going to either love this or hate this by how beautifully simple it is. I'm just going to erase this because I know I'm going to be using the board more as we go. Here's what I'm going to do. I got a list, a big list of things that need to be sorted. So here's what I'm going to do. I'm going to arbitrarily pick a pivot, just some number in that list. Ideally, we want that number to be close to the median value inside that list, but let's not think too much about that right now. I'd pick some arbitrary thing, okay? So I randomly pick it. Maybe that takes order one time because I always pick, I don't know, the 0th element, whatever. It doesn't matter. So I pick this point. I pick this pivot. And then I go through the list. And I put all the things in this n-size list. I put all the things that are less than me over here. And I put all the things that are bigger than me over here. But these things aren't sorted. So here's the algorithm. I partition my list into things less than me and greater than me. And I sort these things. Just sort them with Quicksort. That's it. Just sort them with Quicksort. But you might be thinking, well, hold on, you can't just say you sort them with Quicksort. Yes, I can. Because Quicksort is partition, sort, sort. Append. That's it. So what does that mean? Partition, sort, sort. Okay, so I go to the smaller list over here. That's going to be size, hopefully, roughly half of that. I pick a pivot. All the things less than me, greater than me, sort, sort. Go over here. Pick a pivot, less, greater than, sort, sort. And so on. Eventually, if I keep splitting those lists into smaller and smaller lists, those lists will become size 0 and 1. And we know that lists of size 0 and 1 are sorted. So once I get all the way down, I'll have a whole bunch of lists of size 0 and 1 that are all sorted, and they're going to be like in order. The lists will be in order. It's a crazy idea. So this is just what I just said. Yeah, okay. Here's the idea, okay? I've got a collection of things. I randomly pick a pivot. I pick 14. I go through that collection of things and put all the things smaller on the left. Now, if I have a collection of things of size n, how long does it take to partition that thing? Well, it's going to be order n. I pick a pivot and then put all the things over there or over there. That's n. Then I go down here. Okay, I pick a pivot, it's 8. Put all the things smaller over here, it's 6. Okay, I picked the pivot 6. It's already size 1, so I guess I didn't need to pick a pivot again, but whatever. And if I keep doing this, well, we get like this. We get these series of lists. The numbers in the squares are like steps, so ignore those. Or don't ignore them, but don't think that they're part of the things being sorted. But in the end, we get this. Here's the visualization. If you're having a hard time with this, just take your time, slow down, make it make sense. This is important, it's cool, but this slide right here kind of shows you how we break it down. Again, do note this slide, it creates, like because it picks the pivot, it didn't actually even need to do this because this was size 1, but it doesn't matter. So here's the algorithm. This is really it. I'm not going to go through it, you can go through it. But let's think about the complexity analysis of this algorithm. So, I have to partition. And if I partition, and I happen to pick a reasonably good partition point, where the partition is close to like the median value of the things in that collection, then I will have roughly half of the list over here, and the other half over here. That's the idea. Now realistically, we're not including the pivot, so really, maybe that should be n over 2 and n over 2 minus 1, but we're lazy computer scientists, so we don't care about that. So we've got our pivot, and we've got a list of size n over 2 over here, a list of size n over 2 over here. So partitioning that top list, partition took order n time. Okay? Then I go down a layer, and I've got these two lists that are half of n. How long does it take to sort this one? Not sort, partition. How long does it take to partition the left list? Well, that's n over 2. And how much does it take to partition the right list? Well, that's n over 2. So, like, it's half of n and half of n. I mean, on the second layer, it's still order n. Right? Because I have to do half and half, but in total, I have to partition that one and then that one. There's two things of half n, so it's like order n. And if I keep doing that, how many here? Quarter n, quarter n, quarter n, quarter n. In total, it's going to be like order n. So at each layer, how much work is there? Well, at each layer, I have to partition, and it's order n. But how many times do I have to partition? That's the catch. How deep is this tree going to be? Take a second and think about it based on what we learned about trees. So if we keep going all the way down, we will end up with all of these lists of size 1 or 0 at the bottom. Now, if you're paying attention, we should have on the order of n lists of that size. Because, of course, if we're removing a partition at each time, it won't all be all n, but it'll be close-ish. The key is, I have to do order n work on the way down when we're partitioning. On the way down, I have to do linear amount of work each layer. But how many layers are there? How deep is that tree, or height? What's the height of that tree? Well, it's going to be on the order of log base 2 of n. So I have layers, because the relationship between the number of nodes and this nice binary tree is log base 2 of n. So I have log base 2 of n layers, that's the depth, and for each layer I have to do linear work. So it's going to be log base 2 of n times n. A lot of times we like to write the n out front. That's it. That's for the partitions. And then on the way back up, we have to combine these lists, but that's going to be like linear time for each layer. So I guess it's going to be 2 times n log n. But we don't care about those coefficients. So isn't that cool? Now, this all falls on one big assumption. This assumes that our partition just happens to pick a nice pivot. We happen to pick a pivot that's in the middle such that we get about half the things over here, half the things over here. But I might get really unlucky. Here's the problem with Quicksort. I can get really unlucky where I pick a pivot. In this case, it happens to be the smallest element in that collection. So I put all the things on the left that are smaller than the smallest thing, which of course is nothing. And then all the things on the right, which are greater than. And how many things will be over there? Well, n minus 1, because we keep the partition up. So it's n minus 1. So it's still order n to do one layer. But now, how many layers are there in this tree? How many levels? Well, if you look at this, it should be pretty obvious that there's going to be n levels. N minus 1, n minus 2, until we're done with one thing left. So if we have bad partitions, it's n squared. So it's interesting, because with like bubble sort, we had a worst case scenario of n squared, but a best case scenario of linear. Now, with Quicksort, I have a worst case scenario of n squared still, but a best case scenario of n log n, which is much better than n squared, but definitely worse than linear. So you might be thinking, well, what's the point? But here's the thing, with Quicksort, on average, you end up getting closer to n log n. But let's now look at another really good sorting algorithm. Okay, before everything, I am going to show you something pretty cool. They're called heaps. You're probably going to learn a lot more about heaps next year, but I'm going to show you how we can encode a tree, a binary tree, with an array. So here's what I've got. I'm going to draw my array. I'm going to draw like a Python list, but let's pretend it's an array. And I'm going to put 1, 4, you know what, I'm not going to sort this because that might confuse. I'm just going to put arbitrary values in here. A, B, C, D, E, F, G, there. That's my array. But here's how I can encode this. No, it's not, this is the encoding. Here's how I can decode this, interpret this as a tree. A is the root. B is the left subtree, then C, then D, then E, then F, then G. Let's draw one more just because, H. And then down here, it might be hard to see, but I also have an H. And then that's it. There's no left or right subtree on D, and these are all empty. This is how we're going to encode a tree with an array. This is called a heap. This is a general heap. That's it. That's it. That's all it means. There are interesting things about this heap. One, with this heap, we are guaranteed that our tree, and I always mix up the two words, they're full or complete tree, I can't remember. Point is, I'm guaranteed that the tree is balanced, and I'm guaranteed that it's going to be filled left to right completely, but the last row might not be full, but it will be filled starting at the left to the right, okay? So that's the cool thing. But another really cool thing about this heap is I can traverse this tree really easily. Pardon me, I can jump through this array really easily in constant time to get to my left child and my right child, and also to get to my parent node. So here is the formula to get any given node's left child. The left child is 2 times I plus 1. So let's say I'm at B. Okay? This is index 1. I want to find the left child. Don't even look here. Don't look at this. I don't know what it is. I want to jump to the index that has it. So it's just going to be 2 times I plus 1. Well, I is 1. In this case, I is 1 because it's B. 0, 1. 1 times 2 is 2 plus 1 is 3. Okay, so 0, 1, 2, 3. D. D must therefore be the left child. And of course, it is. This will work for any given node. C. What's its left child? 0, 1, 2. What's 2 times 2? That's 4 plus 1 is 5. 0, 1, 2, 3, 4, 5. F. It must be F. It is. It's guaranteed to work. And if you want the right child, big surprise, it's just that. 2 times I plus 2 will always give you the right child. That's it. That's it. If I want B's right child, 2 times 1 is 2 plus 2 is 4. 0, 1, 2, 3, 4. E. We got it. Point is, I can, in constant time with this little function, if I have any given index, I can get that index's left and right child like that, in constant time. It's fantastic. I can also get the parent with this little expression. I minus 1 divided by 2. This assumes integer arithmetic, so any decimals you truncate, you ignore. But let's say 0, 1, 2, 3. 3 minus 1 is 2, divided by 2 is 1. Well, D's parent must be 0, 1. That's B. Oh, look at that. It is. 0, 1. Let's say it's G. Well, that's 0, 1, 2, 3, 4, 5, 6. What's 6 minus 1? That's 5. 5 divided by 2 is 2.5, but of course we ignore the decimal, so it's 2. 0, 1, 2. See? Yep, look at that. We found its parent. Nice and easy. Wait, did I do F or G? 0, 1, 2. Oh, C. Yeah, G is C. Doesn't matter because F and G have the same parent. Point is, I can jump from a parent to either the children in constant time using this array encoding, or from the children to the parent in constant time. And what's really cool here is I've encoded an array, I've encoded a tree with an array. Before we were using link structures and all that stuff, that was all complicated. Look, you can do it with an array. With this fancy little map, boom, we're done. Isn't that cool? So we call this a heap. Now, we are going to use a heap to sort. And a lot of people love this algorithm because it's actually miraculously simple. So, a heap will be an almost complete binary tree. A tree is completely filled with all levels except lowest level, left to right, yeah? The height of any balanced binary tree with n nodes is, of course, log base 2 of n. We got to remember that. The height of any given tree that's balanced is going to be log base 2 of n, meaning that a heap will always have a height, when you think of it as a tree, will always have a height of log base 2n. Always. That's the rule. The number of levels is going to be log base 2n. So, here's an example of a heap with 9 nodes. In this case, I didn't draw the nodes. The nodes are just at the ends of the line. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Now, a max heap is a special heap. We can also have minimum heaps. But let's talk about max heaps. A minimum heap is the same thing as a max heap, just flip it. So a max heap is a heap that ensures that, now, before anything, it is not a binary search tree. Listen carefully, not a binary search tree. The rule for a max heap is the biggest thing in the heap must be in the root. Okay, here, let me say it this way. All values are greater than or equal to the values in the children. For any given node A, it must be bigger than the children. It's not that, oh, B needs to be less than C and A. No. All that matters is that A is bigger than these two. Or equal to. I guess if we allow duplicates in this example. And all values are less than or equal to the value of its parents. So any given node must be less than A. That's it. So a max heap, A's got to be the biggest. And then I have two more values here. This must be the biggest in this subtree. And so on, and so on, and so on. That's the idea of a max heap. And remember, it's really easy to do a comparison between this node and this node. Because I can go from B to know what its parent is really easily with that function. And I can get to B's children with the left and right child little expressions too. So those are trivial to find. It's easy, it's constant time to find a given node's parent and children. And then I just do a comparison. Oh, my less than or greater than. That's it. So a max heap, the biggest things here, these must be less than A must be greater than these things or equal to, B must be greater than or equal to these things, and B must be less than B, and E must be less than B, and so on. That's the max heap. A min heap would be the same thing, but smallest, and so on, and so on, and so on. So, here's how we build a max heap. We add, so I start with an empty array. I'll leave this example on the board so we don't get lost. But I start with an empty array. And I've got this new element. I've got a collection of things. I've got a bucket of things over here I want sorted. I'm going to add them to my heap. I'm just going to add them to the array. So I go to my array, I pull from the bucket, and I add it to my array. the next spot in the binary tree, okay, so I add that new thing to the next spot in the array. So the first time it's going to be index 0. If that element is larger than the parent, swap them. How long does it take to check if I'm greater than my parent? Well, it's constant time, right? And of course, if it's the start, I won't ever have to do any comparisons because I'm the only thing. But as I build, this question's going to get more and more important, right? So if I add an arbitrary thing here, I'm going to have to compare to my parent. If I'm bigger than my parent, I must swap. Given that the height of the tree, like, okay, let me put it this way. If I add h, I might have to swap with d, right? I add a new value in h. Maybe h is 1 billion. And this is like, none of these values are 1 billion. So I add h. I need to compare h to d, which I can do really easily with that function. If it's bigger, I swap. Then I need to compare what's in d now with b, that billion. If it's bigger, I got to swap. Swap. At most, how many swaps will I have? I mean, it only takes constant time to do a swap. I just have to, shuffle things around. Still constant time. But how many times might I have to do that? Well, what's the height of this tree? Because the furthest this thing could ever have to travel is from a leaf to the root, which is just going to be the height of the tree. And we know what the height of this tree is. It's going to be log base 2n. So at most, I'm going to have, not log base 2n. I'm going to have at most log base 2 comparisons that I have to do. But if I have a list of things I need to sort that are size n, how many times might I have to traverse this tree at the maximum? N times. N log n. Okay, so here's just an example. I add 9, great. And we're going to visualize this as the tree, not the heap itself, but do know that nice one-to-one conversion there. I add 14, this is what happens. But of course, 14 is bigger than 9, so I have to swap them. Done. I add 10. 10's fine there, because 10 is less than the parent, which is 14. I add 6. Fine. I add 17. Well, 17 is greater than the parent, which is 9, so I have to flip them. And of course, 17 is greater than 14, so I have to flip them. And there we go. Now I've got my heap. That 17 traveled log base 2n up. But how many things did we have to add to that tree? Well, all n elements we wanted sorted. So for each n things, it has to move at most log base 2n times. So n log n. So I now know, once I built this heap, I now know 17 is the biggest element, right? I'm guaranteed that 17 is the biggest thing. So if I take 17 out, I've got the biggest thing. Okay, before even thinking about that, obviously I don't have a sorted collection of things yet. But I have 17, and 17 is the biggest element, so I can remove it. And now I know I've got the biggest thing. And after I remove it, I put the last thing into the root. That's the rule. Now, of course, by looking at this, is this a max heap? No, because 14 should be above 9. So we have to fix the ordering of our heap. And this is where we'll just now, where before, when we were building the max heap, we added things at the bottom and we bubbled them up. Now, we have to bubble things down. All we have to do is compare to the left and right child. Swap the largest of the children. So I compare 9 to 14 and 10. Well, I swap with the bigger one because I want to make sure the biggest thing's on top. So I swap the 14 and the 9. There. And now I need to compare 9 to the children. Well, 9 and 6, well, they're fine. how many comparisons here can happen at most? Well, worst case scenario, it's got to bubble all the way back down to a leaf spot. And what's the height of the tree? Log base 2n. And how many times am I going to remove something from this heap? Well, a total of n times. So to build the max heap, it's n log n times. And then to remove each thing to get the next biggest thing, because we got to remove and then swap bubble down, it's log n times n, because I got to take the n things out. Well, that's n log n again. So it's like 2n log n, which is of course just n log n, because we don't care about the coefficients. Isn't that cool? This is just the explanation. Go through it if you're still struggling. Now, merging sort. Merging sorted lists. Here's another sort called merge sort. I'm just going to erase this now. Merge sort requires one of the important notes that we made about Quicksort. The one important note is lists of size 0 and 1 are sorted. We know that. Nothing's out of order. An empty list and a list with one thing in it is sorted. But there's also another new trick here that we're using for merge sort. And I think I've got an example in here. Yes. It's really easy to merge two sorted lists into one larger sorted list. If I have two sorted lists, it's easy to merge them into a new sorted list. That's bigger. That's the combination of the two. So here's the idea. Here's my two lists. Notice that not everything in one list is less than or bigger than. It's just I have two lists that are sorted. I don't care how they need to be combined at this stage. It's just they're both sorted. I want to combine them into a larger sorted list. So here's all we have to do. I start at the beginning. I compare the two, and I take the smaller of the two, and I put it into the new sorted list. Then, for whichever list I took the thing out of, I move the little bookkeeping arrow down. And now I'm going to compare the 2 and the 3. I take the smaller one of the two, add it to the sorted list, and move that little bookkeeping arrow down. So there, and there. Great. Now I compare the 3 and the 4. Well, now 3 is smaller, so I add 3 to the sorted list and move that little bookkeeping arrow down. Of course, when you implement this, if these are arrays, those arrows are going to be indices, just values, indexes. So we have the 3, move the arrow down, compare the 4 and the 5. Of course, 4 is smaller, so we add it, move it down. Whoop, there we go. Compare the 5 and the 7. Well, 5 smaller, move it down. Compare the 7, 8, add the 7, move down. Oh, well, I mean, if there's nothing left in this list anymore, then I just have to take the remaining part of the other list, or array, whatever, and boom, boom, and there we go. So the point I'm making here is if I have two sorted lists, if I follow this algorithm, I'm guaranteed to get a bigger sorted list. It's cool, just merging two sorted lists. So how much time does this take? Well, I guess I'm going to have to compare things. If I have two lists, two arrays, let's see what I have. Do I have it in the slides here? Yeah, okay, merge sort. Given that, it's easy to merge two sorted lists. What's the computation complexity of this? Do I have the example? No, I don't. Okay, let me explain. How much time? Well, if the lists are the same size, and the size of those lists is order n, well, it's going to be 2 times n comparisons, because I have two lists of size n, I've got to do all those comparisons. It's going to be 2 times n, which is, of course, just n. But if they're two different sizes, n times m, no, n times m. If one list is size n and the other one's size m, where n and m are not the same, well, we could think of it in a couple of ways. Well, we could say, well, it's going to be n plus m, really? But of course, in reality, one of these is going to be bigger than the other. And let's say n is the bigger number. So, at most, worst case scenario is n is the bigger of the two lists. At most, n and m are the exact same value, meaning that it's 2 times n work. But of course, we don't care about coefficients. But if n is much bigger, well then it's going to be n plus m, but if n is bigger than m, at most it could be 2 times n, but we don't even care about that coefficient. So we could even still think of it as like order n still. Basically, if, okay, n is bigger than m, bigger than or equal to m. Let's assert that. That's the case. We always make it that n is the bigger one. If n is equal to m, then it's 2 times n, which of course is order n, right? If n is not equal to m, if n is greater than m, that's an m, then it's going to be n plus m, but m is less than n, meaning that n plus m is also going to be less than 2 times n. And if we didn't even care about this coefficient, we still don't even care about the m, kind of. So we can think of it as order n still. There we go. Take your time and chew on that if you're scratching your head. It's not too bad, just slow it down. Okay, so, once we know these two facts, it's basically a very similar algorithm to Quicksort. Split the two lists. I don't even need to pick a partition anymore. Split the two lists. Split this, split that. Split this, split this, split this, split this. All the way until we have lists that are size 0 and 1. Then once I have lists of size 0 and 1, they're sorted. Well, I have an algorithm to merge two sorted lists, which are linear time. And I'll have to merge these lists at each layer of that tree. But how many layers in this tree are there going to be? N log n. This tree, of course, because it's not really a tree, but we visualize it as a tree because we keep dividing by 2, divide by 2, divide by 2, divide by 2. I think I've got a visualization. I guess I don't have a visualization. But it's always going to be just like that Quicksort one, where it's n. Then I divide the lists in half. And so on. How many layers? If we keep dividing by 2, it's going to be n log n, n base log, not n log n, log base 2n. And how much work is it to combine? Well, it's linear at each layer. So linear work, linear work, linear work for each layer. There's log n layers, n times log n times log n. Now, merge sort's better than Quicksort because merge sort doesn't have that little catch of like, well, we have to pick a good pivot. Because the best and worst case for merge sort is still going to be n log n. Or Quicksort, if you get unlucky, it's going to be n squared. So if I were to ask you, of all the sorting algorithms you used, what would you want? Bubble, selection, insertion, BOGO, bucket, quick, heap, merge. I mean, by the way, there's a bunch more sorting algorithms. And I know a bunch of you right now are saying like, oh, I want BOGO sort. Okay, fine. But of course, like of these, the ones near the bottom are better. And earlier, I guess in the last class that I had recorded, I was saying like, well, it turns out you've all been sorting things in your life, but you actually really suck at sorting. Because I'm willing to bet none of you are doing like merge sort. But now I hope I showed you, do bucket sort if you can, I guess. But if your things need to be sorted, do like merge sort. Because merge sort is absolutely going to be faster than the other sorting algorithms you've been doing, like your bubble, your selection, or insertion. And absolutely BOGO. So, yeah, it's kind of weird. And what's crazy to me is people have been sorting things for millennia. But we only formally came up with these better sorting algorithms relatively recently, which is kind of weird because you might think well, something so trivial as sorting, what's going on? Anyways, so that's that. That's going to be the last of the stuff we cover in 162. Take your time, like I was saying in some of the previous lectures, each lecture is more than one class worth of content. So take your time with it, chew on it. You should not expect to watch it and be like, okay, now I know, I'm good to go. No, you're going to have to take your time, chew on it, be patient because of just the constraints we now have. So take your time, but otherwise, that's it. Well done. Good luck on the exam. See you later.